Hi, Mr. Richards here, and today's algebra lesson is on exponential functions. What is an exponential function? Well, it's a function that can be described by an equation of the form y equals a times b to the x, where a is not equal to 0, b is greater than 0, and also not equal to 1. Some examples are right here, but let's deal with our first example now. Graph y is equal to 4 to the x. Find the y-intercept and state the domain and the range. Well, if we make an xy chart, but instead of just a simple xy chart, let's make an x, and then let's have our 4 to the x, and then our resulting y. And let's list our numbers -2, -1, 0, 1, and 2 for x. And let's start with our 0, 1, 2, because I think those are easy to find. 4 to the 0 power is going to be 1, since anything to the 0 power is simply 1. What about 4 to the first? Well, 4 to the first is 4. And 4 to the second power is 4 times 4, which is 16. Now, what about 4 to the -1 power? Well, remember from negative exponents that 4 to the -1 is the same thing as 1 over 4 to the first. Well, 1 over 4 to the first is just 1/4. And then for 4 to the -2, well, remember once again that this can be written as 1 over 4 squared, and 4 squared is 16, so this result is 1/16. And now we can go graph this. We have our -1, -2, if we'd like here, and then 1 and 2. Count by halves going to the left and right. And then going up, we could count by 2s, so this would be 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, when it comes to graphing, let's just start, well, anywhere really, but we could start with 0, 1, which would be right here. And then 1, 4 is right there. And 2, 16 is up here. Now it gets kind of tricky to graph -1, 1/4. Well, that's somewhere kind of in this neck of the woods, and -2, 1/16 is kind of down here even closer. I mean, you really have a hard time to even graph it. Now, as we graph this, we're very, very close to the x-axis and the negative numbers, and then we just kind of shoot up here as we get closer to 2, like this. It looks like we're growing exponentially. But before we get to that, let's make sure we get our y-intercept and our domain and range. And for our y-intercept, where our graph intercepts or crosses the y-axis, well, it crosses the y-axis here at 1. So we can say our y-intercept is 1. And our domain we can write as d, and our domain is our set of x values. Well, it looks like we can use all of our x values, so we could write this as all real numbers. Now our range, R, is our set of y values. Now, will this ever be able to cross this axis and get into the negative territory? Right now this graph just has all positive y's, But is it possible to get a negative? Well, in this example, no, it's not, because no matter how small you get, we're just making it a smaller fraction, getting close to 0, but never crossing that axis. So our range for this would be all positive numbers. Now, let's look at our exponential function. It's in the form y equals ab to the x power. Now, our a right now, it doesn't look like we have it with y equals 4 to the x, but our a here is 1, and that a is greater than 0. What about our b? Well, our b in this question is 4. And b in this case is greater than 1. Well, when you have an a that's bigger than 0, which in this case it's just 1, and a b that's greater than 1, since we have 4, this is what is called an exponential growth function. Since as our x's grow in size, our y's grow exponentially fast. Now in our next example, we have graph y equals 1/4 to the x power. Find the y-intercept and state the domain and range. Well, let's make an xy chart just like we did in the previous example, where we have x, then we would have 1/4 to the x power, and then we have our resulting y. Our x's we can still have -2, -1, 0, 1, and 2. And let's start with our 0, 1, 2, because quite frankly those are just a little bit easier. We have 1/4 to the 0 power, and anything to the 0 power, including a fraction, is just 1. And then we have 1/4 to the first power, which is just 1/4. And then we would have 1/4 to the second power, which is 1 squared over 4 squared, which is 1/16. Now, what about these negatives? Well, there is a rule that goes with these, but we'll walk through it. So if we have 1/4 to the -2nd, well, remember, when we had something like 4 to the -2nd, we could rewrite that as 1/4 squared, which is 1/16. Well, the opposite kind of takes place here. When we have 1/4 to the -2nd, we can rewrite this as 1/1/4 squared. And 1/4 squared is simply 1/16. Now, from there, this is a complex fraction. We have 1 divided by 1/16. And if we keep our 1, change our division to multiplication, and flip the 1/16, we get 16/1, which is just 16. So 1/4 to the -2nd power is 16. Now, when I go to do 1/4 to the -1st power, I'll clear off this workspace here. We have 1/4 to the -1st power equaling 1/1/4 1/4 to the positive first, which is just 1 over 1/4. And again, as a complex fraction, this is 1 divided by 1/4. And if we keep our 1 over 1, change our multiplication to division, or our division into multiplication, and flip the 1/4 to 4 over 1, we get a result of 4. So 1/4 to the negative first power is just 4. So you can notice the pattern there. 1/4 to the negative second power is the same thing as 4 squared. 1/4 to the negative first power is the same thing as 4 to the first. So now we've arrived at the place again where we can graph. So we would have -1 and -2 for our x's, a +1 and a +2 here for our x's. And again, we can count up by 2's, 2, 4, 6, 8, 10, 12, 14, 16, 18. And now, when we graph -2, 16, that would be right about here. -1, 4 would be right about here. We cross the y-axis at 0, 1 right here. Hint, hint, y-intercept. Then 1 is 1/4, and 2 is 1/16, which again, like the previous example, kind of tough to draw. And now, for this one, it looks like we're going in this shape right here. Now, let's go ahead and look at our y-intercept. The y-intercept is once again 1. Now our domain, D, is going to equal, once again, all real numbers. Our x's look like they can be pretty much anything. And once again, for our range, we're all in the positive territory. It does not appear that we're going to cross that x-axis and get into the zeros, because as our exponents grow larger, 1/4 to the third, 1/4 to the fourth, we'll get closer to 0, but we'll never get to negatives. So once again, our range is going to be all positive numbers. Now we're once again with an exponential function in the form y equals ab to the x. Now this time, once again, our a was just 1. I mean, it's 1 times 1/4. And so again, our a is greater than 0, as our rule says it needs to be, or at least not equal to 0. But for our b is a fraction. So our b is in between 0 and 1. And when that happens, this is what's called an exponential decay function. The first example, as our x's got larger, our y's grew exponentially. In this example, as our x's get larger, our y's decrease exponentially. Those are our two types here of exponential functions. And here is a great summary box of the two examples we've just done. Exponential growth functions, you can tell as our x's increase, our function also increases. As x decreases, our function approaches 0 but never crosses it. For our decay questions, as our x increases, our function, our y, approaches 0 but again never crosses. As the x decreases, f of x increases. Now, there are real-world applications to exponential functions, and one is that of depreciation of cars. As our example states, some people say that the value of a new car decreases as soon as it is driven off the lot. The function v equals 25,000 times 82/100th to the t models the depreciation in the value of a new car that originally cost $25,000. V represents the value of the car, and t represents the time in years from the time of purchase. Graph the function. What values of v and t are meaningful in the context of the problem? And second, what is the car's value after 5 years? Well, for this table, it's a little bit more complicated than the previous example, but we'll still have our t, which represents our time in years. That's going to be our x-axis here, t. And then our y-axis is going to be v, which is our value. Now, we'll still evaluate our time for 0 year. I mean, we might as well go 2 years, 4 years, 6 years. And yes, we can use a calculator on this type of question. When you put 0 in for t, well, anything to the 0 power is 1, so 25,000 times 1 is 25,000, which makes sense. When you put 2 in, 82/100 squared is 6,724 10,000ths, 0.6724, times 25,000 is 16,810. When you put 4 in for t, 4 years, then multiply by 25,000, we get about $11,303, and technically 4 4/10 of a cent, but we'll just leave it there. And lastly, if we put in 6 years, 0.82 to the 6th times 25,000 is 7,600 and some change. So let's graph this. For 0, we have 25,000, which should make sense. It's the price of the car. And after 2 years, we drop down to 16,810, which is going to be right about here or so. After 4 years, we're down to just above 11,000, which is right around here. 6 years, we're down to 7,600, just down here. And so we are going down, not in a line, but certainly down in a decay. Now, I went to a graphing calculator to see what this would look like in a graphing calculator, and this is how it would appear. So hopefully now you can definitely see where the decay is, and the graphing calculator certainly helps us to see the decay. Now, what values of v and t are meaningful? Well, for v, I would say that v needs to be less than or equal to $25,000. I mean, all of these are smaller than $25,000, or of course equal to. And for our time t, well, our time needs to be greater than or equal to 0 years. Those are the most meaningful values for v and t. Now, what is the car's value after 5 years? Well, we can substitute in 5 for t. So our function is v equals 25,000 times 82/100ths to the t power. And we can substitute in 5 for t, so v equals 25,000 times 0.82 to the 5th. And after you take this to the 5th power and multiply by 25,000, you'll get about $9,270. So a great real-life application for exponential functions. Our exponential functions lesson finishes with being able to determine whether or not a function is exponential. So determine whether the set of data shown below displays exponential behavior. Write yes or no. Explain why or why not. Well, let's look at our domain values, our x's. Our domain here, well, this is going at regular intervals, meaning 0 to 10, 10 to 20, 20 to 30. They're all increasing by 10. Our range, well, we're going up by 15 and then 37 and a half and then 93 and 75 hundredths. Or you could say, wait a minute, from 10 to 25, I'm multiplying by 2.5. From 25 to 62 and a half, I'm multiplying by 2.5. And from 62 and a half to 156 and 25 hundredths, I'm once again multiplying by 2.5. And so the set is probably exponential, just based on that. Another way, you could always draw a quick graph. In our x's, we can go, okay, that's 10, 20, 30. And for our y's, we could count by, I don't know, 25, 25, 50, 75, 100, 125, 150, and that's still not enough quite, but for a quick sketch to get an idea, when x was 0, y was 10, which is here-ish. When x was 10, y was 25, which is here. 20 was jumping up to 62, which is around here. 30, it jumped up all the way to 156, which is somewhere up there. So it definitely looks like we're going in an exponential fashion just based on the graph. The y's increase rapidly as x increases at a steady rate. I mean, all of these reasons, looking at the domain and looking at the range, and the domain's increasing regularly and the range is not, it's being multiplied. Looking at a graph and saying, well, look, looks like we have exponential growth here. As my x is increasing, my y is just shooting up. And so our y values are increasing rapidly as our x go at a steady rate. So I would say that, yes, this appears to be an exponential function. And that wraps this lesson up on exponential functions. I'm Mr. Richards. Good luck.